Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With 200 gigabit private networking, scalable shared block storage, node balancers, and a 40 gigabit public network, all controlled by a brand new API, you've got everything you need to scale up. And for your tasks that need fast computations, such as training machine learning models and running your CI/CD pipelines, they just launched dedicated CPU instances. And they've also got worldwide data centers, including a new one in Toronto and one opening in Mumbai at the end of the year. So go to pythonpodcast.com/Linode, that's Linode today, to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. And to grow your professional network and find opportunities with the startups that are changing the world, then AngelList is the place to go. Go to pythonpodcast.com/angel today to sign up. You listen to this show to learn and stay up to date with the ways that Python is being used, including the latest in machine learning and data analysis. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Dataversity, and the Open Data Science Conference, with upcoming events including the O'Reilly AI Conference, the Strata Data Conference, and the combined events of the Data Architecture Summit and Graph Forum. Go to pythonpodcast.com/conferences to learn more and take advantage of our partner discounts when you register. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and don't forget to visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers. Your host as usual is Tobias Macy, and today I'm interviewing Itamar Turner-Trauring about what you need to know about running Python workloads in Docker. So Itamar, could you start by introducing yourself?
Hi, my name is Itamar Turner-Trauring. I help teams using Python to ship features faster, and been using Python for about 20 years. And most recently, I've been spending a lot of time focusing on figuring out how to really run Python applications on top of Docker in the best way possible.
And do you remember how you first got introduced to Python?
Yeah, it was 1999, and I was a web developer doing PHP. And I heard about this web framework called Zope, which had a lot of really neat features. It had a built-in management UI, it had a built-in transactional database and object database. So I ended up learning how to use Zope and built some websites with it, worked on a .com where we ran Zope. And then at some point I decided I didn't want to be a web developer anymore, but since Python was a general purpose language, I ended up using Python for a whole bunch of other things like distributed systems and networking and so on.
And so now, as you said, you've been working with Docker for being able to package up and deploy Python applications. And for anybody who isn't familiar with it, can you just start by describing what Docker is and some of the benefits that it can provide to this overall problem space?
Yeah, so Docker is sort of a generic name and the earlier implementation of sort of a set of technologies for running applications in an isolated and reproducible manner. And basically, it lets you take a full file system for your application. So all the files it needs to run, basically a whole Linux distribution plus all your code, and package it into an image. And then you can run that image, and when you run it, it will typically run in isolation in terms of the networking stack, in terms of the other processes you can see. And so basically, it's a little bit like having a virtual machine, except unlike virtual machines, you can run a whole bunch of containers within a single Linux kernel. And so you have less overhead in terms of running lots of Linux kernels. And it's easier to connect if you do need access to the shared file system, it's easier to get to it. But you get the benefits of the virtual machine, which is isolation, and the images let you sort of ship everything you need to run your application's code.
And what was your motivation for dedicating so much of your time and energy into the specific area of using Docker for Python usage in production?
So I started using Docker a number of years ago, 5 years maybe. I worked on one of the early storage backend systems for Docker. So I had a bunch of experience with just packaging applications for Docker. And so at a previous job, I was packaging our code up for Docker, and I was using some of the latest features to try to get smaller images and faster builds, like multi-stage builds. And I noticed that even though we were in theory, we're using some of the Docker's features to make faster builds. In practice, the builds are actually taking a long time. We weren't using any of the caching. Every time we built an image, it would basically build everything from scratch and ignore caching. And so I spent a bunch of time trying to figure out why, and I spent a bunch of time then trying to get our tests to run in GitLab CI, which is what we were running using Docker. And eventually I realized that basically there's a whole bunch of details you need to get right. And many of these details are not written down anywhere. And it can just take people, like, I then spent a bunch of time just doing research to see what else I'd missed. And it's just a huge amount of effort to get all this information. You have to wade through like blog posts that are 4 years old and therefore out of date. You have to log through a whole bunch of tutorials that are using things that are very much not best practices, things are insecure, and that's fine for a first tutorial, but they don't tell you that they're doing the wrong thing. So lots of people just copy them and like end up shipping insecure images. It's one of those areas of ops work where you just have to get a lot of details right, and it's not well documented. And so I figured there was value in spending the time to do the research and then write it up, and so people can learn all the details they actually need to know to make things fast and secure and maintainable.
For the overall use cases of Docker, there's a bit of a divide between people who are using it for their development environments just to isolate different projects and not pollute their laptop or desktop with all of the different dependencies that go into being able to get an application running, and people who are using it for production environments where they need to package up all the code that developers are creating and then be able to put it on their servers for end users to be able to take advantage of. And I'm wondering if you can just talk through some of the differences in requirement as far as the level of effort and detail necessary for both of those different use cases. And since production is your primary focus, some of the common edge cases and issues that engineers run into when trying to take advantage of the production capabilities for Docker.
Yeah, and so if you're using Docker for development environment, and it's kind of nice for that because, for example, whether you're in Windows or Mac or Linux, you can run the exact same versions of the code. On Mac and Windows, it'll run a Linux VM behind the scenes and sort of transparently proxy Docker commands to it. So it's good for that. But you often tend to emphasize things like fast feedback cycle for a developer. So you want, for example, code reload. Every time, like if you're doing a web application, it's easy to just every time you save a file to restart the web application or reload the new code. And so your Docker image will basically be hooked up to the code checkout the developer is working on and reloading from that. Whereas in production, you would actually have a particular version of the code. Another thing, which I actually wrote an article about today, database schema upgrades. If you're working as a developer, developing your code, the sort of natural way to do a schema upgrade is as part of your code startup. So when you start your container, when you start your application, first thing you do is a schema upgrade, and the next thing you do is start your application. That way you're always running on a matched version of the latest code and the latest schema. And for development, that's fine. For production, that can cause problems because if you migrate your schema, database schema, if you migrate your data schema on application startup, unlike a developer environment where there's only one process running, typically in production, you might have 2 or 3 or 4 or 200 processes running your application just to scale across multiple machines. And so now you have 200 processes trying to migrate this database schema at the same time. And unless you're using some sort of database migration tool that can deal with this can corrupt your database because like the tool unless you have some sort of lock, like you can't really migrate your database schema at the same time. And so they do have different requirements. And there's a whole bunch of other details involved in production, like security matters, but when you're doing development locally, you don't really care about security, you care about ease of use. Having a really large image is not really a big deal necessarily because usually the feedback loop is tied to, you're just mounting your code in, you're not repackaging each time. And you're not copying the image around, it's just local in your hard drive. So a few hundred megabytes more don't matter. So the ways in which you use Docker if you want to do it right, are probably going to be somewhat different between packaging for quick developer feedback and packaging for what you're going to run in production.
Yeah, there's actually a great presentation I saw a while ago called Heresy in the Church of Docker that talks about some of those differences in use case, where a lot of people will see Docker and say, oh, it's just this panacea where it solves all of my problems. I just put it in a Docker container and then ship it off to production and I'm done. And then he talks through all of the different layers that need to go into it once you're actually in a production environment, as far as the security, ensuring proper networking, ensuring, distribution across multiple hosts. And so I'll add a link to the show notes for anybody who wants to watch that. But yeah, the overall production, the overall set of issues that come in when you're actually running it in production are a lot more than people might initially suspect. And I'm also curious if there's anything specific to Python itself as far as being able to build containers that are production ready that would differ from just the generic case of Docker on its own.
A lot of it comes down to, for Python, just the specific tools that are different. So if you're shipping a Go binary in a container, like Go basically compiles everything down to one binary. So packaging up Go is very easy. You just copy one file in and you're done mostly. Maybe you need to install a few libraries. For Python, you need the Python interpreter. You need a bunch of C libraries you depend on. You need all the Python libraries you depend on. You need your code. You have different choices for a base image. And again, these issues apply to other languages, but you want to make the Python's, there's different options for Python. There's different ways that people specify their dependencies. So there's poetry and there's pipenv and there's just plain old requirement subtext. And so for those, you want to do things in different ways. And then often you want some level of, you want to install all your Python code into one thing, often that's easy to copy over. If you're doing a multi-stage Docker build, you basically compile things like C extensions in one image. That means you have to install your compiler and so on in that image, and it's very big. And then you add a second image, which is your production image, and you just copy over the compiled code. And so your final image that you run in production doesn't have a compiler in it. That means you're copying a bunch of files over, and Python will, by default, install files all over the place. And now you need to either use a virtual env or do a user install. And so basically, it's not that it's fundamentally different than many other languages. It's just they're just detail and just another small detail, another small detail, and over time it's a lot to keep track of, and it adds up.
And as far as the biggest pain points that you see for people who are getting started with Docker and trying to shift it into a production environment, what are some of the ones that you have found to be at least the ones that are initially most painful that people are trying to deal with, and some of the advice that you have for overcoming those issues?
I guess there's the invisible but potentially extremely problematic pain points of security. And then there's the more obvious ones people encounter. So security is a sort of a whole issue on its own. So maybe we can talk a bit about it afterwards. But putting security aside, some of the other pain points then feed into security problems. So I'll start with the ones that sort of hit people first. Basically, when you're building a Docker image, you are installing, in some sense, an operating system from scratch, and then compiling all your code, and then installing your libraries. You have to install a whole bunch of stuff and build a whole bunch of stuff. And depending on how much compilation you have, how many libraries you depend on, this can just end up being a fairly slow process. And then if building a Docker image becomes a bottleneck in your development process, so you say you have some integration tests that use your Docker image, and now before you can merge a pull request, you need to build a Docker image. If it takes 10 minutes to build your Docker image, then now you've added 10 minutes to your feedback loop to catching bugs, and that can end up being very expensive, especially as the size of your team grows. And then maybe less of a immediate concern, but it feels wrong, is it's very easy to end up with really giant images. And if you have like a gigabyte image, it just takes a while to download. So upgrades are slower, uses up bandwidth. It's not ideal. And so there's ways you can deal with the slow builds, and basically Docker's build system has caching, but that then starts introducing security problems. So if you're caching Basically, the way the caching works is you have a series of steps you're doing to build your Docker image. So you might say, I'm starting with the Ubuntu 1804 image, and then that's step one. And then step two, I'm going to install these packages. And step three, I'm going to copy my code in. And step four, I'm going to build and install it. And since typically only your code is changing, you cache the earlier steps. So you don't reinstall the Ubuntu packages you need every single time. And the problem there is like you can be 2 months in and now you haven't updated any of the Ubuntu packages that you're running in production, and so you haven't gotten any security updates. So you've gotten fast builds, but at the cost of not getting security updates. And so you need a process in place to rebuild your image from scratch without caching, let's say once a week or whenever there's a security update. And often you need build secrets. Another problem people often have is sort of a combination of security, non-security issue is often you need access to some private secret information to build your code. So let's say you have a private Git repository, you can only access it if you have the right SSH key. And the Docker build is sort of an isolated file system of its own, so you have to get your SSH key into the Docker build. But if you're not careful, it's very easy to end up leaking these secrets into the final image. So there's a pretty decent chance that if you go and look at a lot of Docker images that are publicly available that were built from private code, that if you look in the image, you'll find an SSH key or some other secret embedded in the image, and the people who built it didn't even know about it. And there's other annoyances like if you're not careful, it can be hard to shut down your Docker image. Like you'll hit Control-C and then it'll just sit there. And then after 10 seconds, it'll time out and then it'll kill it, because signal handling can be a little bit tricky to get right. And if you don't do it right, then you never get clean shut down. You always get like kill -9 after a 10-second timeout. And there's also things like if you're running in a Docker environment, it might be slightly different than running on the host machine. And so, for example, for Gunicorn, that can result in some cases in Gunicorn web server just freezing for a few seconds because it just expects certain locations in the file system to be actually RAM file system. So, but within the Docker container, they're always on disk. And so anytime your disk is slow, suddenly Gunicorn's heartbeat system is blocked and suddenly Gunicorn just freezes. There's just all these details that you have to get right. And some of them are somewhat unexpected. And I guess, last security issue that people don't often seem aware of is that you really don't want to run your Docker container as root. The default, unfortunately, in many of the official Docker images is to run as root. They don't discourage it enough. And the problem with running as root is it makes it much easier for attackers to escape the confines of the Docker container and take over the machine that's hosting them. So, for example, in February 2019, there was an attack that allowed someone to basically escape Docker and get root on the host machine. And running your container as a non-root user, as an unprivileged user, would have prevented that attack from happening. So for security, the sort of absolute minimum you should be doing when you're packaging stuff for Docker is making sure you don't run as root.
One of the issues that you pointed out in that list is the problem of the overall speed of the Docker builds. And you pointed out the fact that there are multi-layer aspects of the container runtime, and some of that can factor in as far as the way that the caching takes place. And I also know that some of the ways that the Dockerfile syntax works, it can contribute to the overall size of different layers. So I'm wondering if you have any particular advice or general resources or guidelines as to how to make best use of that layering system and some of the potential gotchas of people who are writing their own Docker files.
Right. So I guess I can start with a quick review of the Docker image format and then how that reflects in the Dockerfile instructions for building Docker images. So Docker image is basically a set of layers. For our purposes, you can think of each layer as a tarball, and you untar the first layer, then you untar the second layer on top of it, and then a third layer on top of it. And you can't ever really delete files from earlier layers. You can only hide them. So when you delete a file in the third layer, it hides it, but it's still there on like the second layer, if that's where it was. So we have basically these stacked layers. And these layers allow you to have caching because you have a Docker file, which is the instructions for creating a Docker image. It's Docker file is one word. And each line of the instructions to first approximation matches up to a line and to a layer. So first you create the first layer, and then the second layer, and the third layer. And so your instructions for building might be start with Ubuntu 18.04 base image, which basically says use these previous layers, which are marked as being the Ubuntu 18.04 image. Use those layers as the base layers, and then run apt-get install these packages. So now you've added a second layer, and then copy in some code from the host file system. That's another layer, and then install that Python code. That's a fourth layer. And then as part of the build process, there's caching, where it basically does a hash of, if it's just a command like apt-get install, it hashes the text of the command. So if you haven't changed that line, then it'll consider it not to have changed. And if you're copying files in, then it'll hash the files you're copying in. So if the files have changed, it'll invalidate the cache. If the files haven't changed, it'll be able to look it up in the cache. And so as long as you have a layer in the cache that has the same hash as whatever you told it to do, it'll say, oh, I already have this layer pre-created. I'm not going to rerun that step. And this is useful because to build, if you think about what it takes to install some code, so you have to install a bunch of packages like a compiler and libraries and dev headers, and that takes a while. You might have to download it. You have to installing packages takes a while. And then you copy in your code, and then you install the Python libraries. That might be more compilation, and install your code. And so basically just all this copying and compiling and downloading and whatnot just takes time. And the caching lets you say, oh, I don't have to redo this step. Like I already have, the last time you built this image, you already installed the same Ubuntu packages. You don't need to reinstall them. I already have a layer that has all those files in them already. Ideally, you only rebuild the layers where things actually change. So if only your code changed, you shouldn't have to reinstall any of the dependencies because they're the same. But in order to ensure that happens, you need to make sure you copy in and run the commands in the right order, because once you can't use a layer from the cache, all subsequent layers in your build are also invalidated, so you have to rebuild them. So if the very first thing you do is copy in your source code, and then you install the Ubuntu packages, if the files you're copying in have changed, that invalidates the Ubuntu package install, even though it's completely unrelated to your files. And so when you're writing your Docker build instructions in your Docker file, you want to do things so that the minimal amount of invalidation happens. So first you want to install the system level packages, because they don't depend on anything else, and there's no reason to redo that every time your code changes. And then you copy in just enough of your files to install the libraries you depend on. And this is where some of the Python-specific stuff comes in. You might be copying in requirements.txt. You might be copying in a pip file and the pip file.lock, depending how you are managing your dependencies. And then so you copy in your requirements.txt, then you install those dependencies. And now if your requirements.txt doesn't change, you won't have to reinstall those dependencies because you'll be able to use the layer in the cache. And only then do you copy in your code. And by having that almost the last thing you copy in, if your code changes, it only invalidates the last couple layers. And you can reuse all the cache layers that have all your dependencies and all the system packages and so on.
Another element that plays into this whole layering piece is the idea of the base image that you're working from. And I know that there can be issues as far as consistency in terms of the way people tag those base images, where the latest might actually not point to the same container, or even the specific versions might not point to the same container, depending on how the original creator decides to construct their workflow. And there are also issues with security problems contained in those base images that don't necessarily get addressed or that aren't necessarily obvious. And I'm wondering what your opinions and advice are as far as how to address that overall problem of where to start in terms of building your containers. Is there a particular distribution that works well, or just general best practices around what to do for your base image for what you're then constructing on top of?
as a starting point, and there's always specialized cases where the situation is different, but for most people, you want as a starting point to have an image that's based on an operating system that has some level of stability. So it's not so the libraries of chips aren't going to change radically from one week to the next because it just increases your maintenance burden. So Ubuntu long-term support releases are a good base image in that sense, whereas Ubuntu's non-long-term support are less so because those get updated every 6 months and suddenly all your libraries change, whereas the long-term support ones, you'll have stability for a couple of years. So you want to start with something like that. So Debian releases also get supported for stable Debian releases get supported for 5 years, I think the latest one. So you want to start with a operating system that's an image that's based on an operating system that's very stable. And then you also want to have usually a particular version of Python. And if you say you're using the current long-term support Ubuntu, which is Ubuntu 18.04, that ships with Python 3.6. If you want Python 3.7, it's not installed and you have to get it from somewhere else. And so to solve that problem, there's an official quote-unquote Docker image for Python, which is basically Debian stable. And specifically, they now have Debian stable Buster, which was released middle of July 2019. So it's actually very up-to-date packages, and it's going to have security updates for the next 5 years. So it's sort of, right now it's quite up-to-date, but you also can trust it to be stable. And then they install on top of that particular Python versions. And so you can get like Python 3.5 or 3.6 or 3.7. And the way you select that is in addition, each Docker image has sort of the name of the image and then tags. And tags can point at different underlying images. And so one way you can, when you build your image, you can refer to it in a bunch of different ways. And one way is you can say, I want Python 3.7 off of Buster, which is the latest Debian release. So 3.7 Buster, or if you want a slightly smaller image, 3.7 slim Buster. We can link to this particular image in the show notes, just so you can see the different options. And if you link to 3.7, that means at some point there'll be a new point release of 3.7. So it'll go from where it is now, 3.7.4 to 3.7.5. And you'll automatically switch from 3.7.4 to 3.7.5, which, if you're not too worried about breakage from that minor of a version release, then you can do that. Or you can say, I'm going to specifically build on 3.7.4, then I know exactly what Python version I'm getting, and with the cost that you have to notice when 3.7.5 comes out, and manually change your Docker image to refer to that. And this gives you a decent amount of stability. If you really, really want to be sure that the particular image you're building off of doesn't change, Bitnami also packages Python Docker images in this style. But one of the things they have that the official images don't is that they will actually have permanent tags, where they'll say, we guarantee that if you refer to this tag, we will never, ever change what it points to. Whereas the 3.7.4 Buster tag for the official Docker images could, in theory, in fact, it does get rebuilt every once in a while when ever there's a new release of pip, for example. They change that. So if you're worried about a new version of pip somehow breaking your build, you can use the Bitnami images and then link to one of their permanent tags and as your base image, and then you'll know that it'll never change. The more stability you have, the downside of that is you're not getting security updates. And so it's always best practice, as when you're building the image yourself, is that one of the commands you run is updating all the system packages. So you say, in addition to doing, if you're using a Debian or Ubuntu system, in addition to apt-get install, you also apt-get update to the latest packages, just to make sure that you have the latest system packages. And again, if you're using caching, that will only happen the first time. So it's also best practice to once a week, or if you're paying attention every time there's a security list, or if you're really paranoid once a day, rebuild your images from scratch with no caching, and that way make sure you always have the latest system packages. And just one final note about choosing a base image is a lot of people recommend Alpine Linux, because Alpine Linux gives you slightly smaller images. However, I actually personally think it's a bad idea to use Alpine Linux because they use most Linux distributions use GNU libc as a standard library for C programs, including Python, and Alpine Linux uses Muscle, which is a different libc. And it's just different, and so there's all kinds of edge cases in there that haven't been fixed, or that are different and cause different behavior. And so you'll see reports of like Python crashes because it has a different, smaller stack size, or string formatting for timestamps is different, or weird edge case DNS differences. And Muscle has been fixed over the years, and all the known bugs that I've heard people talk about have been fixed, but someone had to notice this problem and report it, and they had to fix it. And so if you're using Alpine Linux, we're more likely to have weird, obscure production problems. And the benefit is you save, say, 80 megabytes, 100 megabytes on your image size. And personally, I feel that production impacting problems, especially obscure, hard to debug ones, are a thing I don't want. I'm willing to have another 100 megabytes on my image, not to worry about that.
One of the other things that has been introduced to the overall Docker ecosystem in the past few years are alternative build tools that issue the Dockerfile syntax in favor of some other way of actually constructing the containers. I'm wondering what your opinion is on that overall trend, and if there are any particular tools that you have experience with and how they compare to Dockerfile itself.
It's on my to-do list to do deeper research into these, and so I would consider some more of a preliminary. But the problem with the way Docker works is that it's a daemon that's running on your computer, and then the command line tool you use sends commands to that daemon. And that daemon is running as root. And so that results in a bunch of operational issues. There's in CI systems, they'll often sort of restrict the way it can run, or CI systems already running Docker has its runtime environment. So they have to run Docker in Docker, which adds to some weirdness, like because you have this daemon, which is in a container off to the side, and it can be pretty confusing. In particular, if you're using GitLab CI, you should read the Docker and Docker instructions they have very carefully. And Circle CI won't let you run Docker containers the same way. And so one alternative route people have taken is, which I believe the Podman project. The Podman project basically emulates the Docker command line fairly thoroughly and completely. So it can package Docker files, you can do Docker run, you can do all the different commands that you can do in Docker, except it's implemented not as a daemon, but as a command line tool that just runs without a daemon. And so that makes it simpler and easier to run, and you don't also need to run as root often. And on my to-do list is seeing if that makes some of the CI build issues easier. I believe also that the downside is that it doesn't, whereas Docker, there are solutions for running it on Windows and Mac. I don't think you can run Podman on Mac. Again, I have to do the research, don't take my word for it. And then there are sort of different approaches which sort of abandon the concept of a Docker file altogether. So one option is Nix. Nix is an attempt to make a packaging system where all builds are completely reproducible. So instead of saying, I'm going to use this Debian package, and hopefully it's exactly the same as the Debian package I referred to last time, and this Python package, and hopefully it's the Python package I had on last time. With Nix, you are guaranteed that you're getting identical inputs because of the way it works. And one of the things Nix can generate is Docker images. And so if you really care about reproducible builds, Nix seems like the sort of a tool that is designed for that from the start and does it all the way from the level of system packages. Basically, everything is, you're not using Debian or Ubuntu packages, you're using Nix packages. And so it gives you reproducible builds end to end, and it can generate a Docker image. And I know there's some efforts also, again, getting rid of Dockerfile altogether, which sort of emulate the build pack concept that Heroku popularized. And so they're trying to build similar build pack systems for Docker where you don't have to go and do everything yourself. It sort of knows how to package things for you. And that means you take away some control, but it also mostly just works. And then there's a fourth approach, is something that I've actually tried to build. This is a product I've created, which is a template for Docker packaging for Python applications in production. And the template approach is sort of a halfway between what Dockerfile gives you, which is a huge amount of flexibility, but also a huge amount of places where things can go wrong and details you have to get right, and a tool where a higher level tool sort of restricts what you can do in some sense because it's giving you a higher level abstraction, and there's a reason you have to deal with all these details when you're building things. And so the idea with the template is that it gets you, for the majority of people, the majority of time, you don't have to edit a Docker file. You just edit a simplified config file, and that does everything, and it does all the necessary security checks and security settings, and it makes sure your images are small and so on. But when you hit the edge case it doesn't support, you can fall back to the lower level, more flexible thing and just edit the Docker file, edit the code to customize it. And there's a few other tools I'm forgetting about that people are likely to encounter. Basically, what started out as Docker is now a bunch of related semi-competing technologies that approach things in slightly different ways.
What are the cases where Docker itself is the wrong choice for a production environment? And are there any useful alternatives that you have seen that address some of the same problems that Docker is intended to cover?
So for some applications, you're only running one application, so you don't care about the isolation aspects of Docker, and you already have a system with VMs. So you can just build a VM and image, the tool packer, and then run it on machine in the cloud, like Google's cloud or Amazon's cloud, and get the same sort of benefits of isolation and reproducible builds, and potentially then you can use it to like Vagrant to run the image locally. So you can get some of the same benefits without using Docker, and then Docker adds some level of performance overhead, and so not that big. I would guess it's a few percent, but it basically, you don't have that, and so it solves that problem. If you consider Docker as a specific instantiation of a container technology, like all the things you've been talking about are basically generically, Docker is a specific implementation on the idea of containers. And so there are other implementations of container runtimes, for example. There's Rocket, there's one other, I don't remember its name, and typically they can run Docker images, and so there might be operational reasons or security reasons you don't want to run the Docker daemon, but you can run a effectively equivalent technology. And similarly, there's runtime systems that ingest Docker images like Heroku or I believe Elastic Beanstalk, and their runtime, it's proprietary software. We don't know what it's running. The runtime is plausibly not Docker. It's just reading the Docker image format. But you can just build a single binary executable with a tool like PyInstaller. And if you're distributing command line tools or software people will run the desktop, like technically you can use Docker for that, but it's really not and container. The idea of containers makes a lot of sense for that, but the user experience of Docker is not really designed well for command line tools. So you probably don't want to use Docker for that. And something like PyInstaller might be a better choice if you just want to install like a isolated thing people can run, or things like Snap or Flatpak if you're distributing stuff for Linux distributions. And yeah, it's sort of for development environments versus like, I guess another approach is Conda, where Conda comes with a package that it's its compiler, and it comes with precompiled C libraries. And so you can basically have a runtime environment that's in terms of available libraries and binaries that's different than your host operating system, but it's still just, there's no, it's not a container, it's not isolated from the host operating system, it's just Conda provides a different set of compilers and libraries for you. And so you get some of the benefits of having more control about what specific libraries and packages and so on you're running without having this isolation that might make things more difficult if you need easier access to your host file system.
The overall space of Docker and running Python in production is pretty vast, and we've only touched some of the preliminary aspects of it here. But are there any other aspects of this topic that we didn't discuss yet that you think we should cover before we close out the show?
Yeah, I guess the thing that I want people to pay attention to is that much of the documentation and examples you'll get for this are often not best practices, and to some extent that's less of an issue if it means like your build's a little slower or your images are a little larger. But for security, that's actually can be an extremely expensive problem. And so at least for the security aspects of packaging stuff for Docker, you should just make really sure that you're doing it right. And even the official Docker recommendations, like they were sort of half-heartedly say you should not run as root, but then they make other recommendations that would force you to run as root. And you really, really don't want to run as root. It's just, it makes the ability of attackers to escalate their access much higher. And in general, just don't assume that if you found a random Docker tutorial and went through it, you know how to build images that were good enough for production. Like the security issues, at least, it doesn't take a lot of work to get it right, but you do have to do that work, and the vast majority of tutorials will just completely gloss over all the problems you're going to have, like making sure your caching doesn't lead to insecure packages and not running as root and so on.
All right. Well, for anybody who wants to get in touch with you or follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And with that, I'll move us into the picks. And this week, I'm going to choose the movie Shazam. I just watched that, and it was very entertaining and amusing, and had a good time watching that with my kids. So with that, I'll pass it to you, Itamar. Do you have any picks this week?
I've been watching Veronica Mars, the original 3 seasons, and it's sort of interesting seeing a TV show talking about sort of class conflict and income inequality, especially a TV show that at this point I think is 15 years old. And it's also just a fun mystery/teenage drama combination.
Well, thank you very much for taking the time today to join me and share your experiences and knowledge of using Docker for running production workloads with Python. It's definitely a very relevant subject and one that I think a lot of people will be able to benefit from. So thank you for your efforts and your time, and I hope you enjoy the rest of your day.
Thank you. Thanks for having me.